Hello. Uh, Welcome to this tutorial session on SPCOM 2022. We have distinguished speakers with us, Jean-Francois Chamberland and Krishna Narayanan. JF Chamberland is a professor in the Department of Electrical and Computer Engineering at Texas A&M University. He completed a Bachelor of Degree at McGill University, a Master of Science at Cornell, and doctorate at University of Illinois, Urbana-Champaign. His research interests are in communication and information theory, statistical inference, computer systems and networks, data science, and learning. Recently, he has been studying the efficient design of wireless systems and fundamental limits of communication networks. His contributions have been recognized through an IEEE Young Author Best Paper Award from the IEEE Signal Processing Society and a Faculty Early Career Development Award from NSF. He was invited to present educational innovations at the Frontiers of Engineering Education Symposium. He served as Associate Department Head at Texas A&M and as an Associate Editor for IEEE Transactions on Information Theory. Krishna Narayanan received his B degree from Coimbatore Institute of Technology in 92, MS from Iowa State University in 94, and PhD degrees from Georgia Tech in 98. Since 98, he has been with the Department of Electrical and Computer Engineering at Texas A&M, where he is currently Eric D. Rubin Professor. His research interests are broadly in coding theory, information theory, and signal processing, with applications to wireless networks, data storage, and data science. His current research interests are in the design of uncoordinated multiple access schemes, coding for distributed computing, exploring connections between sparse signal recovery and coding theory, and analyzing data defined on graphs. He's passionate about technology-enabled teaching and innovative pedagogical approaches. He was a recipient of NSF Career Award in 2001. He also received 2006 Best Paper Award from the IEEE Technical Committee for Signal Processing and in 2018 Best Paper Award at the Conference of Vehicular Electronics and Safety. He served as an associate editor for coding techniques for transactions of information theory, and also area editor for coding theory and applications. And also in IEEE Transactions and Communications. In 2014, he received the Professional Progress in Engineering Award given to an outstanding alumnus at Iowa State University. He was elected IEEE Fellow of IEEE for contributions to coding for wireless communications and data storage. And I would also like to add that JF and Krishna Narayanan, they received with a co-author Best IT SOC and ComSOC Joint Paper Award this year. Congratulations, and we welcome you to present this tutorial.
Thank you. Thank you so much for this generous introduction. Also, can you give me a thumbs up on my vocals so that I make sure the sound is good? Okay, very good. So the first thing I would like to do is I would like to thank you for being there. I understand that there's both some people online and there's a room with people there. So for questions, I guess they'll come from the audience. It's a pleasure to be at SPCOM again this year. I think for me, particularly ISC is a special place because partly of the quality of the researchers there, but also it's a very welcoming environment. And I'm glad that I'm able to be part of SPCOM 2022, albeit remotely this time. I am especially honored because I was invited by Professor Chandra Murthy to be part of give a tutorial. And I think I would like to underline the fact that he's a good example of a person that conducts award-winning research at ISC. This year, they were given a prize for the 2021 Jack Wolf Best Paper Award for SIT. His student Lakshmi Ramesh, Chandra, and Himanshu were received the prize. And also, maybe this is not known, but one of my former PhD students, Santosh Kumar, came from me he was a student at ISC under Chandra, and then he came to Texas A&M. And then later on with his postdoc advisor, Henry Pfister, won the IT Best Paper Award. And finally, there was a mention that Krishna, Vamsi, and I won the joint IT ComSOC Paper Award this year, and Chandra was an associate editor for that paper. So that was a cornerstone as he helped us get that paper in better shape. So I'm very grateful for that. as well. And of course, finally, I'll mention that ISC has Paramo, one of my former students, who was doing quite well there. So it's a bit of a homecoming. The first thing that I would like to do, let me share my screen or start the sharing process, is mention that the slides are available online. So if you would like to get a copy of the slides on your computer to take notes, that's possible. And also you can get the LaTeX source if you're interested later on. This work that I am going to be presenting today, now it's a tutorial, so I'll be presenting a lot of work as a disclaimer that's not my own. I will present results that are pertinent to unsourced multiple access. But the part of the work that I did in this area is with my esteemed colleague, Krishna Narayanan, and we have several students who work with me and Krishna together on these problems, including Jameson, Mihail, Vanzi, and Avinash. So that's a very exciting field and rich field for us. I should also acknowledge our sponsors. So we've been quite successful with the US National Science Foundation for the line of work on unsourced multiple access. And also I would like to acknowledge some support from Qualcomm Technologies through their university relations program. This is the roadmap for the tutorial. And while you look at it, what I would like to say is this is really an opportunity for you to ask questions and be interactive. I know this is a bit of a challenge if it's because it's an online talk, but I will be trying as much as possible to monitor the chat room on a different device, and as well as feel free to interrupt, raise a hand, and have the host ask a question on your behalf at any point during the talk. And that way we can make it a little bit more interactive. There's the technical roadmap for the talk. I want to talk a little bit about unsourced random access, give a motivation, and talk about how it's related to support recovery in very large dimensions. And also, I want to talk about ways to handle the complexity of these problems, in particular, sparsifying collision, data fragmentation, and towards the end, present some new results on spreading in tensors. And then on the mathematical side, I will talk about several techniques that are useful to reduce complexity or to address very large problems for which we need low complexity algorithms. And some of that includes graph-based constructions, concatenated codes, data fragmentation, which is a divide and conquer approach, the rise of approximate message passing as a tool for very large problems, fast Fourier transforms and fast transform techniques in general, and information propagation. And this underpins some of our work, but it's pervasive through an area for which we have very large problems. So hopefully you can both learn the area that we're going to discuss today, but also get some of the tools that are pertinent for large problems that transcend the area. And then the last thing is I want to say is we had a chance to give a tutorial at SPCOM a couple of years ago. And I've tried to make this tutorial with minimum overlap. So the part of the work and the area that I talked about last time has little overlap with what I'm going to talk about today. So if you are a repeat attendee to the tutorial, welcome again, and hopefully you'll learn something new. Okay, so let me get started with the motivation. The quick motivation for the area for unsourced random access comes from the realization of three facts. So the work is sits squarely in wireless systems. So by that, I mean that we're going to be discussing wireless technologies. And we are going to be talking about systems in a new way or a different way. And the reason that I am motivated to look at the problem differently comes from three realizations. The first fact that I want to talk about arises from cell phone penetration across the world. So there are now more active cellular subscribers than there are humans on the planet. So of course, some humans have more than one phone, But in general, we're reaching a point where market penetration is essentially extended to anyone who wants a phone has a phone. And this is important because the future of wireless then cannot be in growth from subscribers. At least it cannot exceed population growth on Earth. The second realization that I want to touch upon is the fact that for a long time, screen quality and video playing was a driver of throughput in wireless devices. So over generations of phones, the screens were getting better. And when you have better screens, it means you need to transmit more data to have a good image. Now, with the latest generation of phones, we're slowly reaching the visual acuity of the people who have the best eyesight in our society. So in particular, if you have 20/20 vision right now, which means that, among other things, that you can discern very low angles, you have to hold the phone at a distance of slightly less than 2 inches or maybe 6-7 centimeters to be able to start to perceive the dotted screens. And this is partly why some of the virtual reality glasses are based on phones, because they're reaching the visual acuity of the human systems. So the second consideration then is that hardly throughput and growth in wireless can hardly come from better screens at this point, since we've reached the capacity of the human eye. And the third thing is how we interact with phones. So we already interact with phones extensively. These are some of the US numbers here. 63% of all Americans, all traffic online comes from smartphone and tablet users. And more than 70% of YouTube viewing happens on mobile devices. And 65% of digital media time is spent on mobile devices. And we're already at a place where, on average, we spend more than 4 hours on our mobile phones, collectively on average. So again, there, it's hard to argue that we want people to spend a lot more time on their phones. So growth in wireless has to come from somewhere else. This is a summary of the points that I just mentioned before. The growth in market penetration is near saturation. Screen quality is at the limit of eye acuity, and content-rich applications are watched by users for already an average of more than 4 hours. And so what's next? And what's next is kind of the road plan that coincides with the 6G deployment. So if I look at this graph that I've plotted here, on the x-axis, we have device density, and on the y-axis, we have throughput. And this is mainly for downlink. And I have, in this notional diagram, I have partitioned the feasible region into 4 different sections. And the gray one is the present section, where you have fairly high throughput and a certain device density. And if I think of the future of wireless, it's going to be surrounded by these other regions. The first region that we look at is the top green region. That's the hyper-connected region. And that contains things like extreme or extended reality. So it goes beyond virtual reality, hologram, and digital replica. And this seems to be like some of the applications that are mentioned by different providers, including people like Qualcomm and Samsung. And in my view, this is the extension of how we know how to deploy wireless system. So higher throughput we can gain with a cellular system that has more antennas and more bandwidth. So the roadmap for the green region is kind of laid out, and it's kind of clear in many researchers' mind. It doesn't mean that there's not work to be done. There's much work to be done, but that roadmap is somewhat clear. And then we go to the red region, which is a lower throughput region and a lower device density, but that region is the ultra reliable and low latency communication. And this is applications where you have control loops over wireless. If you're thinking about equipping kind of an industry with wireless systems instead of wire, you need very, very low delays to be sensors in the loop or wireless sensors in the control loop. And so that region is also a challenge. And for instance, Parimal Paraga's work on that region, so with some very nice work. And the region that I want to talk about today is kind of the blue region. It's the one where the device density kind of explodes, and the throughput is somewhat all over the map. And it's the massive machine type communication, or at least that's the way people portray that region into 6G. And we'll talk about something that is not in this graph. This notional diagram is based mostly on downlink, supporting downlink application. We'll work on uplink a lot because that has received less attention. So why do we want to distinguish this MMTC region from the way humans interact with wireless systems? So conventional systems that are used by humans have a certain profiles. From a machine point of view, or from a wireless system point of view, humans tend to create sustained connections. And this wireless presentation is a good example of that. We're going to send packets for a long time. So if we're in a wireless environment, it would be sustained. But also large emails, wireless videos on demand, uplink streaming, those are all connections that take place over a very long time. If you download a file that's a few megs, or if you have a kind of advanced internet application, it's also a connection. And one of the things that we do as system builders to handle this connection is we do scheduling decisions, traditionally based on two things. If you believe in opportunistic scheduling, you do it based on the current quality of someone's channel and their queue length or their delay in service that they've received. And you do some combination of the two, and then you do opportunistic scheduling based on that. And implicitly, as part of this process, you have an acquisition phase where you have to ask devices, somehow you have to find out what's the quality of their channel, and also what is the length of their buffer. And that effort that you're making to know and start to get information from a device perspective, you're investing resources, but it's amortized over a long connection. And so you benefit from that greatly. When we start talking about machine-to-machine communication, things are slightly different. So their machine interact with the world at the same speed, about approximately as the speed that a computer schedules jobs on its own core. So you're now talking about small packets, either sensing or actuation or updates, and you're talking about decision that must be taken at the millisecond scales or lower. So this is very different. And another thing that machines don't do is they don't necessarily create connections, long connections. Maybe they just want to communicate a small packet that contains a sensor reading or an alert, or they want to synchronize with another machine. So they do not interact with the world the way humans do when they operate a machine. And in particular, that leads to a phenomenon of a sporadic single transmission from a large device population. So you have a large population out of which only a few devices will decide to communicate, and typically it's for a small payload. Now, I should be clear that I'm not arguing that all machines will interact with the internet that way. For instance, if you do video surveillance over wireless, then you're going to create a connection. And that is fine, because as system builders, we already know how to handle that. We'll do it the same way we handle video connections from humans. But I will argue that it's worth exploring how to do this type of traffic well, because this is very likely to grow quite significantly over the next few years. So spending time understanding the implication of machine type communication is important. And I want to argue for the fact that machine may be inclined to send small payloads. So, and I'll throw it back to one of the paper that came out of my PhD dissertation, and say that one of the main messages of this paper is that for the purpose of inference, if you have a distributed system, most of the information is contained in the first few bits of a payload. So you don't necessarily want to send a large payload. This favors having a very small payload with more connections. And now let me give you a more credible source. This is delta sigma modulation that says, if you track something, maybe you want to send a small signal or a small update very frequently, as opposed to waiting and sending very precise update. So the sigma delta modulation is a paradigm that is used extensively for signal processing. But if you translate the lessons that we've learned from sigma delta to wireless system, then you get the type of behavior that I was arguing for IoT devices. So then what is the problem with dealing with MMTC traffic? Well, the problem has to do with the fact that it breaks the traditional acquisition estimation scheduling paradigm. And it breaks it in the following way. So on this slide, on our left, we have kind of the traditional traffic. So here is a human-based connectivity traffic, if you will. And on the left side, the cost is the cost in terms of spectral resources and energy resources that I, as a system provider or wireless system provider, that I invest to acquire the channel quality and the buffer length of a device. So it's a small cost. And then on the right, you have the reward. So because you are using long connection and the channels are slow moving, you invest a little bit and you get a lot of reward for your investment. If you go to a IoT types machine type traffic, what's going to happen is you're going to have a whole lot more devices, and most of them will either have no packet or a very small packet to transmit. And what happens is if you ask them the same question, the question being, what's the quality of your channel and how much information do you have to send? So most of them, they'll say, I have nothing to send. And a few of them will say, I have a very tiny packet to send. So if you look at the cost of that, because of the device density being much higher, the cost has now grown significantly. And the reward is tiny because you're not amortizing the investment into a long connection. So this is a paradigm that shifts, and if you do it at scale, it breaks the wireless system the way we know. So we need to look at alternatives. And this has been noticed by several researchers. And one of the way that we know that has been noticed is there's been quite a revival that predate on source random access into uncoordinated access or random access in general. And it leads to a new reality. So we must address the fact that machines are sporadically gain the channel. They're not going to establish connection. You're going to have a very large device density, and you're going to have a small set of devices at any point in time wanting to communicate. And that set will change very rapidly from time to time. They are sending small payload, and this precludes opportunistic, it precludes the traditional way to do things. So to address this situation, people have looked at opportunistic scheme or random access scheme instead. So this is the lesson that we'll try to address. We'll look at schemes that are tailored to that type of traffic on the uplink. Are there any questions? Okay, it seems.
Audience here. I think there are no questions in chat as of now. I don't see any.
Okay, so if there are no questions and the sound is still good on your side.
Sorry, Jeff, I did not get you.
I was asking if the sound is good on your side.
Okay. It's fine? Yeah, yes.
Okay, very good. So our first order of business is to think about the what are the implication of the unsourced random access paradigm. And so for the first section, we'll talk about a connection between unsourced random access and compressed sensing or support recovery. And we're going to try to understand the challenge that URA brings in that space, partly because it's a special type of compressed sensing problem. We'll see that. And we want to also review some candidate strategy to address this situation. So the random access is the following. So you have several devices, and typically they're going to use an encoder, and they are going to grab the channel in a random fashion. And as the decoder, you try to recover these messages. And the numbers that we will use for our presentation, there's at least at the beginning, they're derived from the LoRaWAN standard. And so we're talking about a number of devices per cell that's between 25 and 300. And we're challenging ourselves with a small packet of maybe on the order of 128 bits. And we'll try to do that to serve this community of user with this packet length in about 30,000 channel uses. But we'll make a twist out of it. And the twist is that we will use an unsourced match. So the problem with having device using their own encoder, so each having a different code book, is that you need to first decide which device is active and then use that code word. A different way to think about the problem is to have every device use the same code book, and in which case, you do not need to infer which devices are active. You can just seek to decode jointly the messages that they've transmitted. And part of the philosophy of looking at unsourced scheme is the fact that if you do need to know the identity of the sender, then they could choose to embed their identity as part of the message, in which case you would recover both the identity as well as the payload. So it's a slight shift on uncoordinated access, but it leads to some connections that are very interesting. So the way we'll look at it is we'll have no personalized feedback. All devices use the same code book, so we don't need to know who's active. There's no explicit knowledge of identities. And at the end of the process, the decoder is responsible to recover an unordered list of messages that were sent. So again, if we need to know who sent what, then they have to embed their identity in their message. Otherwise, the decoder is not responsible for saying who sent what. They just produce an unordered list of messages it has received. So mathematically, this model looks like this. The received signal Y as a vector is going to be equal to the summation of all the transmitted signal plus some noise. And the twist is that the transmitted signal Xi from device I only depends on the message. It cannot depend on the identity of the device. And as such, we call this problem unsourced because the identity is not known or not revealed. And this line of work was popularized by Yuri Polyansky in 2017, where he was looking at bounds for a new perspective on massive random access. And in his traditional style, he has some theoretical achievable bounds for this problem that we will use as a benchmark, as a loose benchmark for the practical schemes we'll develop. And when I say that it's random access, it's not completely random. There's still some structure to it in the sense that we're allowing ourselves to have a frame structure. What do I mean by that? The access point or the base station will have a beacon, and that beacon will synchronize frames where devices can transmit. So think of it this way. It's not sending a personalized message to any of the device. Rather, it's using a global beacon to say, this is the beginning of a frame. This is the end of a frame. And then potentially it could do something like at the onset of the frame. It could use also a bit of time to estimate the device population, the number of active user, and then maybe report on the slot count. In this image, I've decided to show a frame that's partitioned into slots, but that's not necessary. That could be there or could not be there. It depends on the scheme that we want to use. Now, the same set of device will be using the entire frame. So once a frame is set, there's just a subset of all possible device that reveals itself as possible transmitter, and they use that frame to transmit their message. Okay, so now we have a kind of a multiple access type framework where on the left we have devices, each device produces a message. And as before, they use the same encoder. So what is transmitted by a device only depends on its message. It does not depend on the device identity. And they are added up over a multiple access channel. And what I want to do at the beginning of this section is to track what happens to one of the messages. So we'll look at only one message for and one device to begin with. So every device employs the same codebook. And that codebook is a function that transforms a bit string. So here I write a bit string as set01 raised to capital B, where capital B is the number of bits, into a signal that's being transmitted. So let's see how this translates into or can be mapped into a compressed sensing problem. So what I want to do here is to think of the mapping from a binary message into a signal as a mapping into a column vector. So here I'm starting with the all zero message. I'm using my encoder F. This gives me a signal, and I'm writing this signal as a column from top to bottom, where at the top you have the earliest symbol, and as you progress down, you have over time the symbols that are transmitted by the device. So the mapping from one message gets into one signal. And what I'm going to do is I'm going to compile the signal dictionary. So I'm starting with the all zero signal, then I progress to the all zero, but the last binary digit being 1. That gives me a different column, a different signal. I'm going to stack that as the second column, and then I'm going to proceed with the binary message this way. And as I map the different message, I get a signal, I get a new column every time. And if I do all of them, then eventually I'm going to get a matrix where every column is a possible signal that's transmitted by the device. And this I can do for any encoding function. There's nothing particular or on source about this process. It's just a mapping from binary messages to signal that I stack as a matrix. So what's the relation between that and sparse recovery? So one of the things that I can do then is to create an index, what I'm calling an index vector on the right. So that index vector is an all zero vector, except that it will have a 1 at the position, the integer position of the message. So for instance, the message here at the top would be all 0. This is all 0 and a 1. This is all 0, 1, 0. And this is all 0, but 1, 1 at the end. So I put a 1 there, 0 everywhere else. And as I fold my message index over my signal dictionary, I get the signal that's being transmitted. Hopefully, this is clear. So now if I think of the progression, I think of the progression in 3 steps. I start with the binary message. I transform this message into a message index, where the non-zero entry in my message index is an integer interpretation of my binary message. And then my message index picks my column in my signal dictionary. Now we're ready to look at the compressed sensing analogy for on-source random access. If I have k devices, like it is shown at the bottom, and all these devices use the same encoder, it means that they are using the same signal dictionary. So they have the same blue matrix. And when they add up over the multiple access channel, what effectively, or one way to view that is that their signals are going to be added over the real numbers or over the complex channel. But another way to view that is that their index vectors are going to be added up. So here, if I have 4 devices that are sending different messages, then I'm going to have an index vector that's the sum of 4 basis element, it gives me a vector with 4 non-zero entries. And now if I take that vector with 4 non-zero entry and fold it over the signal dictionary, I get the output of the MAC channel. So let's look at that a little bit more in detail. So again, my model is that, at least for now, we'll come back to that maybe later, but for now it's a fully synchronized system. My receive vector Y is my signal dictionary phi times my sum of the index vector S plus some noise. And S is k sparse, where k is the number of active devices. The shape of my matrix is the height of the matrix is the number of channel used. So say, for example, approximately 30,000. Here I picked up the nice number, but approximately 30,000 channel use. And the width of my matrix is 2 raised to the number of bits in my message. So if I have a tiny message, the width of the matrix would be 2 raised to the 128. And our noise will be additive noise. So if you think of unsourced random access with all devices using the same code book this way, so the same code book means they have the same signal dictionary, then that's exactly a sparse recovery problem. What I have to recover is the indexes of the message on the right. And this is a noisy compressed sensing problem because I have additive Gaussian noise. So naively, you would want to say, okay, so unsourced random access is a compressed sensing problem. Compressed sensing has been studied extensively. So I'm done. I can just use a compressed sensing solver and decode my unsourced random access using compressed sensing solver. So if you think about this, maybe as a personal note, I will ask you a question. Maybe this is a tutorial, so I will ask you a question. If you are online, maybe you can try to answer in the chat, or if you're in the room, you can turn to your neighbor. I am not sure this will work, but let's try. What I'm going to ask you is, how wide a matrix can an API'd out, off-the-shelf compressed sensing solver, how wide a matrix can it handle? So think about that for 30 seconds. And if you're brave, put that in the chat. Okay, so with no visual feedback, it's difficult for me.
Oh, okay. Yeah.
Is anyone taking a guess in the room?
Yes, they are. So the question is, what is the size of the matrices, measurement matrices, right? So
the question is, if I wanted to use an off-the-shelf compressed sensing solver, how wide a matrix, or how tall a sparse vector could I handle?
Yeah. Any guesses?
Okay, so I don't want to put anyone on the spot, so I'll give some measurements. But if you add a vector that's, if you want to use something like, say, an NLS or something easy, then maybe you can go to a few tens of thousands, hundreds of thousands. If you are using a special compressed sensing structure that uses fast matrices, maybe you can handle 2 to the 20 on a commodity computer. But it becomes very hard to go much beyond, say, 2 to the 20. And here we're dealing with a matrix that is much bigger than that. It has a width of 2 to the 128. And I find it interesting to think about this because from a communication perspective, 128 bits is tiny. Like, we code for messages that are much longer than that. So if you view communication problems as compressed sensing problem, problems, they are huge, they're humongous compared to what we can handle with compressed sensing solvers. Okay, so our goal then is to have some strategy to be able to take this support recovery problem that is super wide into practical algorithms. Okay, so talking a little bit about compressed sensing.
I have a question.
Yes, absolutely.
About on the previous slide, you had the size of the measurement matrices, right?
Yeah.
I think I understand how the size has come to be. So.
Okay, so let me tell you this number here, 32,768. That is the number of symbols that I'm allowing myself to use for my wireless uplink within one frame. So it's quite a large number of symbols, 30,000. It's on the order of what LoRaWAN would use, say, for instance.
Okay.
The second number is the following. So I'm thinking of a message that has 128 bits. So when I do the translation that we saw here, where I go from a binary message to a message index. So remember that the message index is all zeros except for one location. And the location where it's non-zero can be thought of as the integer location when this binary message is read as a base 2 integer. So if I view it that way and I build my signal dictionary, then that will have a width of 2 to the 128.
Sure. Yeah. Thanks.
Another way to think about it is if I have an encoding and I give it 128 bits, how many signals can come out of that encoder? 2 to the 128, one for every possible message. Yeah. So that's the width of the matrix. Okay, quick review of some compressed sensing notion. A lot of compressed sensing problems, at least asymptotically, are determined based on two parameters. One is undersampling, and undersampling is the ratio of the height of the matrix over the width of the matrix. So here is the number of channel use divided by the number of columns that we have. So for us, for instance, channel use would be on the order of 30,000, and the number of columns would be on the order of, say, 2 raised to the 128. The second parameter that's often used for compressed sensing is the sparsity. And the sparsity is, in some sense, it's a measure of signal complexity, is the number of non-zero entries in my vector divided by the number of samples. So here, for our problem, K is the number of active devices, and N is, say, on the order of 30,000, the number of channel uses. And now I'm going to use a notional diagram, or rather, I'm going to use a true diagram that comes out of a paper by Donahoe, Maliki, and Montanari that gives you a phase transition for compressed sensing with a certain algorithm, but I'm going to use it just as a notional diagram to illustrate what I mean about our problem. On the x-axis here, we have the undersampling fraction, so delta, and on the y-axis, we have the measurement of sparsity that I talked about. And for many problems, what you do is you see that certain algorithms have a phase transition. So if you think of the undersampling sparsity as a point, if that point is low and to the right, the problem is easier. And for certain algorithmic problems, you will be able to get exact recovery. But as you go upwards or to the left, you get into a region that's much more difficult to handle. And in fact, you're guaranteed for these algorithms to, this is the failure region. Your algorithm cannot recover that. It's a notional diagram for us because these curves are for true compressed sensing problems. And they have either strongly positive or between plus and minus 1. And these curves correspond to the performance of approximate message passing, which is not quite what we'll do. But to think about our problem, we're sitting in that corner, the 0, 0 corner, where both our undersampling fraction and our measure of sparsity are at 0. So it's not clear how these curves behave at that level. And so it gives us some slack to build some system, and that's what we'll try to take advantage of.
So one question again, sorry.
Yes.
So what happens between the two regions? There's failure region and there's exact reconstruction. I can see some the area between.
Okay, so this figure is a little bit misleading. There's one region that's determined by the red curve. And that's the boundary between failure and exact reconstruction when the entries in my vectors are strictly positive. And the blue one is the boundary between failure and exact reconstruction when you have positive and negative entry.
Okay.
So the blue compressed sensing is slightly more difficult than the red one, and that's why the curves are different. Thank you for the question. Okay, so what are our options? Our options would be to do something like classical coding techniques or classical multiple access techniques. Collectively, the community, the communication information theory signal processing community has been very good at designing wireless access in the traditional way, as we can see from our own cell phones. And what we have here is traditionally, if we have multi-access, for instance, here we have two users, then we could decide to have one code book for the first user and one code book for the second user. And then you would have a multiple access channel that looks like this. But the problem for us is that we'll have a lot of devices that are active, and we don't know which device are going to use which code book. So this leads to some serious problems. So we're not able to do joint multi-user decoding, or at least it's going to be computationally very, very demanding if our device population is very large. And we also have the second factor that's not there in traditional communication, where you have to identify which code book are being used right now. So this is the challenge of unsourced random access, and it's a drawback. That's why we don't see too many traditional approaches to solving that problem. The second approach is to say, I'm going to do a divide and conquer approach. And the naive divide and conquer approach would be, say, I am going to take my frame and I'm going to partition it into slots. And what I'll do is I'm also going to partition my index vector. And depending on where the message falls in the index vector, it's going to have use a particular block of access. And in Spirit, what this does is it changes the huge compressed sensing problem into a succession of smaller compressed sensing problem. So this would be nice. The drawback is that actually the size of the matrices, they remain super wide. In particular, if you're going to use, so if you have a matrix whose original size is 2 to the 128, even if you use 16 slots or 32 slots, the width of any of these matrices is still, 2 to the 124 or 2 to the 123. They're still huge, and you cannot use compressed sensing, off-the-shelf compressed sensing problems for that. And the other thing is you don't know how many, if you were to use this approach, you would not know how many devices are in each compressed sensing problem. So you're creating a new issue with this particular approach, or a new way to have uncertainty. And then the next way to do things is something that is somewhat more familiar, and that's you're going to do stochastic binning here. So one way to think about it is to say every device that's active is going to use a slot and only transmit during that slot a coded message. The set of active devices are going to make an individual decision, and they're going to pick one slot each. That individual decision can be made, say, based on the message they're wishing to transmit. And what happens is that you're building a transmission graph where, in some cases, one device can pick a slot, but you can have multiple devices pick different slots. So if I look at this particular graph, what I have from left to right is I have n symbols. This is my total symbol allocation for one frame that I've now partitioned into 5 slots. And at the bottom, I have active devices. They're all using the same code book again, but their code book says, depending on the value of the message, you're going to transmit in only one slot. So here, device 1 decides to use slot 0. Device 2, 3, and 5, they use slot 2. And device 4 uses slot 4, just based on, this is not pre-coordinated, it's random access. And the randomness in the graph you're creating is based on the message you wish to transmit. And this idea is actually what led to the first low complexity scheme for unsourced random access in 2017. That was a very short paper about how to possibly use a scheme. And what they do is they say, we're going to aim to be able to decode a certain number of devices per slot. So if you're below this bar, so in this graph, there's a bar that's at 2, and you're using an error correction code that enables you to jointly decode 2 users at most. So if you have 1 or 2 users, you'll be able to recover the messages. But if you have 3 users, your code is not powerful to do joint decoding on 3. So you're losing these. And what that leads to is something that I call the Poisson wall. So it leads to the following phenomenon. You are going to have to aim for a certain number of devices that you can decode. So on the top left, I have a graph. On the x-axis, I have the number of devices that pick a particular slot. So we'll have just one slot in mind. When it's 0, then 0 devices decided to transmit on that slot. 1 is 1 devices, 2 is 2 devices, and so on. 3, 4, and 5 is the number of devices. I also have to pick the code rate that they'll be able to use, and I have to come up with a particular decoding scheme. So for this particular graph, I said that I'm going to code at a rate where I can decode 3 or fewer devices at once. And I have the ability to do joint decoding for 3 of them. So if there's 1, 2, or 3 devices that are using that slot, that particular slot, I'll be able to decode them. But unfortunately, if there's 4, 5, or more devices who pick that particular slot, then I will not be able to decode them. Okay, so then the next observation comes from these dotted areas that are above that I call missed opportunities. And the missed opportunity comes from the fact that if you're using a code rate to be able to decode 3 users, then when there's only 1 user in that slot, you're coding at a rate that's now excessive in some sense, or you're only able to get 1/3 of the information bit you could have gotten otherwise. On the right, I have a graph that is a Poisson distribution. And the Poisson arises from a limit of a binomial distribution. If I have a very large number of devices and each device, based on their message, picks a particular slot at random, then for one slot, what I have is I have a binomial distribution of devices that has picked that particular slot, say slot 0. And then if in the limit, this will turn into a Poisson distribution. So that's why I call the Poisson wall. And when you combine these 2 graphs, so you have a distribution that's Poisson on the right, and you have the reward that you're getting in terms of information bit on the left, then what you rapidly get is that you get an expression that there is no perfect way to partition your system. So what do I mean by that? Typically, you'll be limited by complexity. The best you could do is to have all the users pick a code book at a certain rate and do joint decoding. But if you have 100 devices, you're not going to be able to do that. So rather, you're going to limit the maximum number of devices you can jointly decode. And when you do that, based on how many slots you put within a frame, you get these curves on the bottom right that are the maximum throughput that you can get based on the number of slots, as well as based on the number of or the number of devices you can jointly decode. And you can see that, okay, so the top curve that starts very high and goes down meets the Shannon limit of the multiple access channel that's shown as a dashed line. But this, of course, warrants that you're able to decode all the devices jointly. The other curves, as you decrease the number of devices that you're able to decode jointly, then the performance decreases, and you should petition for more slots. This is a fundamental limit on how this random access scheme, where you pick one slot per device, can do.
Jeff, there is a question.
Yes.
Can you give the mic if that is okay? Let's see if it is a bit better.
Jeff's simple question. This seems to be some balls and bins problem, that the strategy you have to use is a random strategy, and you have certain number of bins to which you're throwing each ball you have.
That's correct.
So can we use any of the, so a random strategy actually gives you log m by log n kind of load distribution, and you're essentially saying if you do something different, you can do better than that. So I'm somehow missing that connection between what we know from the balls and bins problem and what you're doing.
Okay, so it is a balls and bins problem, and I'm going to look at the graph on the bottom right. When I say slot count, that's the number of bins that you're creating.
That's correct.
And so it's an unusual problem in the sense that you can create more bins.
Yes.
And then at the top, you have your reward, depending on the number of balls you place in a bin. So in gray is 1, 2, 3 is a linear reward based on the number of bins. And then there's a limit on the joint decoding. So if you exceed that, you lose the ability to have a reward for that bin. So it's an unusual ball and bins problem. Yes.
So you want to maximize the number of balls you can create for yourself, so that each bin gets 3 balls. That's essentially it looks like.
That's what you would want to do, but because that's true, but because it's random access,
right,
then you're forced to have a Poisson. So for this particular problem, you would that's exactly what you're doing. You maximize the number of bins to have 3 balls in some sense, but it's a little bit more complicated than that, because if I create more bins, then I have fewer symbols per bin in some sense. So that changes my reward in terms of Shannon capacity for that particular bin too. So it's a little bit more complicated than that, but I think the intuition is correct.
All right, thank you.
Thank you for the question. I appreciate that. And then another way to do things is this data fragmentation that we'll come back to, but the naive data fragmentation is that divide and conquer, where I have k devices. At the top, I have a message of 128 binary information bits. I'm going to divide that into small, say 16 length, 16 bits. And the reason why I want to put 16 bits packets instead of using 128 is because 2 to the 16 is amenable to CS solver, whereas 2 to 128 does not work. And now that I've fragmented my information message into small pieces, and I can do a compressed sensing, I can use a compressed sensing algorithm to recover the list for that. But that's not the whole story, because here what you get is you get 1 fragment per slot, and you don't know which fragment from the first slot goes with which fragment for the second slot, and so on. So there's a stitching problem or a disambiguation problem that has not been resolved with this particular data fragmentation approach. So in summary, what I want you to get out of this is that if you think of one source random access, then what you have is a noisy compressed sensing of an easier kind, because it's a support recovery. So here in blue, again, you have the signal dictionary, and on the right side, you have the index vector of the active messages. The width is huge, so it's a slightly different compressed sensing problem in the sense that it's much greater than normal problem. And there's also an opportunity to view this same problem as uncoordinated access that produces a stochastic binning if you decide to go with a slotted strategy. So possible URA, so we're going to use a mix of them. There's sparsifying collision, through a graph. There's some coding and spreading, and there's some data fragmentation. We have not seen a practical scheme that works yet, but these are the blueprints of what we'll look at next. I think here I can point to some pertinent reference, and maybe this is a good point to ask if anyone has questions about where we're going. Okay, I think there are no questions. I'm also monitoring the chat, so if you want to drop a question in the chat, that's fine.
So
Was there a question or no?
my question is that here we have chosen that the feedback will not have any from the channel. So how does it impact the throughput for our system? And second thing is when we are randomly allocating the devices, so there are a lot of slots which are not having any data for any device. So the situation where we need more throughput, in that scenarios, there are some slots we are wasting. We are not assigning any device to those locations. So is there anything like we can reuse those slots for any kind of multiplexing, or if it is getting wasted, so for the 5G scenarios, how this wastage, how we can utilize it?
Okay, so I will answer the second question first, because I forgot the first question already. The second question is, yeah, so you're absolutely right. There are slots that will have no device in them. The problem is don't think of it as a central entity allocating the device. Devices are picking slots at random. And so naturally, there will be slots that don't have devices. In fact, if you believe in the Poisson distribution, every slot will have a Poisson type traffic, and that traffic leads to slots that are wasted. Now, would there be some scheme that could reuse that in some sense? Probably, but we're not buying to this model yet. We'll look at schemes that are more, in some sense, more clever and more efficient than this. So I think you have a good point about reusing slot. Maybe there are some compression schemes that could be used, but let me present some practical schemes before we entertain that. The second one was about feedback. So right now we're talking about systems that have their best effort. So if you think of the equivalent of the internet, we're really thinking about a UDP type system, not a TCP type system, where it's a best effort traffic. We'll seek to recover the sent messages with high probability, but there is no feedback in the picture. At the end of the tutorial, I will talk about feedback mechanism, both as some ideas that we have for feedback, but also as an open research problem that would tie into with what could you do with feedback. So not a totally satisfactory answer yet, but it's a very good question.
So will there be any kind of trade-off for the throughput, or we are exactly matching the throughput according to the requirement?
Yeah, I will ask you for some, maybe I can talk a little bit about some of the schemes that we have in mind, and then maybe I can revisit that question about the throughput. Because your question may be answered just naturally by the presentation.
Thank
you. But thank you. Maybe if I don't circle back to it, please remind me. Okay, so the first technique that I want to talk about is something that is sparsifying collision in my mind. For in the context of unsourced random access, what we want to do is sparsify collisions from different devices, and we do that so that we can do joint decoding in an efficient manner. So I cannot do joint decoding for 100 devices, but maybe for a few devices I can do joint decoding. But I also want to think about sparsifying collision through graph-based technique as kind of a major theme that underlies much of the research on complex systems. And so the approach I want to take is to review 3 scenarios where graph-based techniques have been hugely successful, and then at the end I will tie this back to unsourced random access. So this is the first way that we're going to do our quest for low complexity. I want to draw much inspiration from probabilistic graphical models or factor graph, however you call them, and in particular, low complexity algorithm like belief propagation. And I'll pause because there is a question from the audience.
Actually, I have a question. Like in the first section, what is the effective operating rate of that encoding scheme?
For the previous scheme?
Yeah, the encoding scheme you have presented. What is the effective operating rate? And what about the decoding scheme?
I will plot it on graph at some point for the throughput. But at this point, I don't want to spend too much time on it. I don't have a straightforward answer because I know it's not a very good scheme, so I don't want to spend too much time on it. But there will be a graph soon, and that will show the performance compared to other schemes. So I'll just pause on that for a second,
okay,
for a few slides. I want to show that graphical methods have been huge in at least 3 different ways for us in communication, and especially in unsourced. And these 3 ways they are the cornerstones of LDPC and LDGM codes. So low density parity check codes over erasure channel is the easiest setting. But they have also been used in a very clever fashion for designing low complexity compressed sensing. And they have also been used to build good graphs for random access. And Chandramurthy is one of the people who made that happen. So I'll circle back to his work as well. So what I want to say is this is a very valuable tool for low complexity system. And not only is it a valuable tool, but it is also a very well studied tool with a lot of success. So the representation that I'm going to use is kind of a Tanner representation. And I'm going to use an example from low density parity check codes over erasure channel. And what I have in mind is the graph in left is a number of variable nodes on the left side and a number of constraint or check nodes on the right side. And then we'll send messages from the variable nodes to the check nodes loosely. And what I want to, one of the performance criterion for how good a graph is at doing certain things will be things like the left degree distribution or the variable distribution on the left from an edge perspective. And also on the check node, you'll have something that's similar, the right degree and the degree distribution from an edge perspective on the right. And I think many people may have seen this, so I'm not going to spend much time on this particular problem, but there's an illustration of these applications. And one of the, conceptually, one of the breakthrough was this idea that you can unravel this bipartite graph into a computation tree. And if that computation tree is does not have local loops or it looks like tree-like locally, then you can essentially do the analysis on the graph as if it was a complete tree and forget the fact that your graph is going to have loops. And in some sense, to be able to do that, you can view that traditionally when we talk about, say, LDPC graph, we say that loops have to grow at a certain rate with the graph. So in an analysis that looks at graph ensembles that are larger and larger, and you're trying to control the contribution that comes to a node from its own message that was sent through a loop. Okay, so why are erasure graph easy? Because of the following. An outgoing, okay, so when you get a variable nodes, if the variable nodes learn its value from any of the edges, then it will know its value. So all the bits have to be erased for it to not know its value. And for a check node, if one of the incoming message is erased, then you're not able to compute the parity of this node. So in other words, the outgoing variable message is erased if all incoming messages are erased, and the outgoing message, check message, is erased if any of the incoming messages is erased. And what you have when you do this analysis is you have two nice equations that you can then fold into something called an exit chart. So on this exit chart, you have the two equations that we saw from the rules that are happening with the graph. Here, the graph is assumed to have these properties that or the graph ensemble, so that the loops are going down with time. But you draw these two functions, and one is the function that comes from the variable node, and one that comes from the check node. You draw one of them is flipped, and then what you can see is you can see if you'll be able to decode the message by seeing if these lines touch or if there's an opening into it. And here I drew an example where there's an opening. And so if you look at an ensemble, then you will keep track of, on the x-axis, of the probability that the particular message is erased. And on the y-axis is the probability that the outgoing message from a check is erased. And what you have is you start from a point, and then you compute the probability or the distribution of the number of erased message from the variable nodes, and then you go to the check node. And if there's an opening between the two curves, then you go to 0, then you know you can decode. Now, I will say this, I am hoping that many of you have seen this before. The one takeaway point that I would like you to have from this particular characterization is the fact that we have many tools to know how to design good graphs. I think that's the most important point as a user of graphs. So that's the first application, LDPC codes, also LDGM codes. Then the second application is sparse graph for support recovery. And so what we have here is we have the following problem. This is a traditional compressed sensing problem. We have a very large sensing matrix, and we have the ability to design that particular matrix, and we have to recover the values of the sparse vector that's on the right. And we do that based on the measurement. So a classical compressed sensing problem, but what we would like to do is be able to do it very efficiently. So the first thing that I want to say is that when you talk about doing a compressed sensing problem very efficiently, then what you mean is that asymptotically, this order of what you need is known. So here, K is the sparsity of the problem, and if K is little o of n, then it is known that the number of measurement that you need to have, or random measurement that you need to have, necessary and sufficient condition is this K log n over K type order. So this is the benchmark that we would like to do, but we would like to be able to do this with a low complexity scheme. Well, it turns out that graphical methods were used by these other Lee, Yin, Pidarsani, Power, and Ramchandran to design very efficient matrix, compressed sensing matrices. And it was also followed up by Vem, I know Avinash, but okay, Tenkarai, and then Krishna, my co-author, to bring down the orders. If you look at the Ramchandran construction gives you to order K log n, and Krishna's construction, along with all the co-authors, gives you K log n over K. So this is the limit that you're looking for. Now let's look at the construction of the compressed sensing matrix and its relation to a graph. So on the right here, I have a graph. Again, I'm using kind of a bipartite construction with some variables on the left and some check nodes on the right. And what I'm going to write, A is going to be my bi-agency matrix of that graph. So that's for bipartite graphs, essentially you're going to have the following. So if I think of a column, so here I've highlighted the first column as blue entries. It corresponds to this variable node. And you can see that there's two edges linking the variable node, and that's where you have a 1. And likewise, this bi-agency matrix, if you think of it from the check node, then that would be the last row here in red. That check node has 3 edges, and these are the non-zero entries on the last row. So you can you have a correspondence between this bipartite graph on the right and this bi-agency matrix on the left. But that's not enough. So you would like to be able to do a little bit better than that. And what you're going to do is you're going to use a tensoring construction or tensor-inspired construction. And what I have to do is I'm constructing this bi-agency matrix A with the same number of non-zero entries per every row. So this is, in some sense, it becomes a regular graph. So if you look at every column here has 2 1s and every row has 3 1s. So it's a very regular graph. And what I'm going to do is replace, I'm going to go row by row and replace the first entry in the row by the first column of this S matrix here. The S matrix is in some sense an error correcting code. And so if you look at this, the first row has 1 0 0 1 0 1. So here you have +1 -1, that's the first entry in S, then you have 0 0 0 0. Then you have the second entry in S that's going to be over here. And then you have the 0 0 in the third entry. And you're going to do something similar to that. So you're generalizing a graph to something that is contains per operation on the check node some sort of compressed sensing. And what you can think of is now if you have a vector that's on the right, because you can construct what you're doing, you will be able, so if you have a real vector, so now we're going to think of a vectors of real entries with a support that is continuous, then you'll be able to decide if within that range there's a 0 entry, if there's a single entry, or if there's a double entry, and or 2 or more entries. And the way you're going to do that is if there's 0 entries corresponding to the first expanded column, then the output is going to be 0 0, and there's nothing much you can do. So you know that there was no entry. If there's a single one of them, then the 2 entries are going to have the same magnitude, and through the sign you'll be able to recover the value of that entry. And if there's more than 1 entry, then you will know because they'll be non-zero, but the magnitudes will not match. Roughly speaking, that's the idea. And so based on that, the same way they're able to design compressed sensing using the same set of rules and do low complexity based on, so here you can also do some sort of peeling decoding. So it's very nice that you can use the same type of graphic tools to design a compressed sensing matrix. The third example that's very pertinent for us is traditional random access. So here we can, if you have devices, you can, we have the following. So this is a setup that is similar to what we were talking about earlier, except that now I'm going to allow every device to transmit more than once and to pick several slots.
Hi, Jeff. This
So
is
you have,
question here.
okay, I will take the question.
Yeah, can you hear me?
Yes.
All right. So if you go back one slide, you're customizing a matrix. What's the objective towards that you're working towards designing such a matrix?
So this matrix was designed to be able to have so you want to have the right number of samples to be able to recover your sparse recovery. So you want to hit that n log k or n log n over k. So that's the first requirement, that it achieves that. The second requirement is your complexity to be able to recover your vector. So if you look at the complexity of traditional compressed sensing problems, it becomes very prohibitive for very large matrix. But this particular matrix is amenable to a peeling process that's similar to message passing in some sense. You operate over pairs of observations. But what you're able to do is you're able to peel and reconstruct your vector in a very low complexity fashion. So you have one of the lowest complexity methods for compressed sensing. And the way you peel is when you're able to recover. So suppose you have a singleton within a row, then you're able to recover where it was, and then you go and cancel it from the other place where it had interference with other users. So it's a complexity reduction approach.
Yeah. So is there some structure to this matrices you're looking for? So what
there's a lot of structure. You have to build a graph that's conducive to peeling, and you can analyze the structure of the graph you want to peel in, and you also want to pick the right kind of enhance or generalized operation that's based on this coding scheme. Yeah, so there's a lot to unpack here.
So the question I'm coming to is, given if you change the number of circle nodes and number of square nodes, do you have to do this by hand again, or there is a nice systematic way of, if I give you the...
you do not do this by hand. There's a nice systematic way to do it.
Oh.
Yeah, because you're going to build like huge matrices.
Yes.
No, absolutely. There's a nice theory for these things, and you do not have to build it by hand at all.
Thank you.
And the construction depends on the sparsity that you want and the number of measurements, but it's very methodical. Okay, so here, this is a random access with a bit of a twist. So you have a slotted system, but now you have the ability for device to pick more than one slot. And what you're going to use is you're going to use successive interference cancellation. So that if a device has picked several slots and you decode it in one slot, you'll be able to do this. And this idea has been around for a little bit of a while, but one of the beautiful connection was identified by Jean-Luigi Levi is to say that the graph you're building through these random access is essentially very similar to an LDGM code over an erasure channel. So you can leverage tools from coding theory to build these graphs in a structured fashion from methods that we know a lot about. And so, this paper here by Jean-Luigi Levi is very interesting, and you can push these ideas to a little further with coded slotted ALOA, for instance. And this one I will do because I had the slides. I will do this one and show how the peeling process works. But the peeling process is similar for the three cases. So the peeling process I'm showing now is for this random access, but a very similar peeling process for the low complexity compressed sensing is there, and a very similar peeling process for LDPC code is there as well. So here in this example, I have 5 devices. Is there a question? Okay, there's no question. So here in this example, I have 4 devices, and they randomly pick some different slots. So if I look on the bottom row, I have device 1 who decided to transmit only once. Device 2 decided to transmit 3 times. So I have packets in slot 1, 3, and 4, and so on. And what's going to happen is I'm able to decode when only one device has transmitted in one slot. So here I'm able to decode the message from device 2 from slot 4. And once I decode it, I'm able to peel the effect of that message from the other slot where device 2 transmitted, which is in this case device 1 and 3. And now slot 1 only has one residual message, M3, so I can decode it and I can peel it. And I move forward with this process. It reveals message 4 from device 4. I can peel it, and then at the end, I have recovered all the message through this peeling process over the graph. And so this is this connection that enables us to design things for very low complexity algorithms. So back to unsourced random access. So I would like to do the same thing for random access. So here I have the sensing matrix. This is the problem that we're familiar with. What happens when we do this slotted structure is we get devices will randomly pick slots. So I now divide my frame into slots. So remember that the length of my frame was the height of this dictionary. And now that I've divided into 4 slots, then now I've divided the height of my dictionary into 4 slices that correspond to slot 1, slot 2, slot 3, and slot 4. The devices, depending on their message, will transmit in, say, for this example, 2 slots, and they will transmit an encoded message. And what happens is when I fold this vector of active messages over my slotted matrix, I get something that is very similar to this peeling process that I had for the random access. And this is how you can use a low complexity graph-based scheme for unsourced random access. There's a little bit more to it than that when you do random access. So one of the challenges is that when you do random access the traditional way, it's typically assumed that you have very long messages. So you can embed in the message the identity of the other slots where you transmit it, and that allows the receiver to go and do successive interference cancellation. But when you have 128 bits, then it becomes expensive to carry that. So one way to fix this is to do a quick compressed sensing to say I'm going to transmit into these slots, and then do kind of a random access for the other slots. So you have some tweaks that you have to do for the unsourced random access. And in terms of complexity, what you would like to do, say you're using an LDPC code, is to use the same decoder for all of them, but you have to introduce a permutation structure to be able to scramble your code across slots. So there's a little bit of, I would say, tweaks that you need to do to make that a possibility or a possible scheme for unsourced random access. So in the first scheme that we introduced, we had a compressed sensing problem to identify the pattern and the permutation of your code, and then the rest is kind of a joint graph that you decode. And now I come to the first graph on performance of unsourced random access schemes. So hopefully I can circle back to earlier, there was a question about what is the throughput for that scheme. So typically schemes for unsourced random access have been so we abide by a common task framework for the single antenna, where the metric is the requirement in terms of energy, EB over N naught, for 30 or so channel use and 128 slots. 128 bits per message, I should say. Okay, so here on this graph, on the x-axis, I have the number of active devices. Of course, when I have more active devices, the problem becomes harder. On the x-axis, I have the minimum requirement in terms of EB over N naught. My performance target is that I should be able to recover up to 95% of the messages. So I'm allowing myself to drop 5% of the messages. And then we can look at the different scheme. The scheme at the very top is the one that is based on random access, where each device transmits once. So this was the benchmark, the first low complexity scheme that came to be in 2017 and was looked at rapidly by Polyansky and Ordentlich. Now, the scheme that I presented, where we have multiple transmission over the graph, so it's a graph-based scheme where we have a little bit of a compressed sensing to tell you where the packets are going to be, and then you have this graph-based with successive interference cancellation. I have these 2 lines. I have the blue lines with squares, and I have the red line with these diamonds. And the difference between the two has to do with the complexity that I'm allowing for joint decoding. This is going to change the way I construct the graph. The red one, the maximum complexity is an ability to decode 2 users jointly, and the blue graph is the maximum decoding complexity is jointly decoded for users. So it's more complex. The dash line that's behind that says fourfold ALOA, that's just an ALOA type scheme where you just allow yourself to theoretically decode up to 4 users. It's not a practical scheme. It was a benchmark that we were trying to match and compare ourselves to say, if you decode only 1 packet at a time, what's a fundamental limit? So this fourfold ALOA for a complexity of decoding of 4 users is the fundamental limit. At the bottom there's 2 schemes that we're going to revisit at some point, but what I want to show is that although when red and blue were introduced, they were the best, more modern schemes that have been introduced since 2018. They do much better. And then the dash line is the fundamental limit that was introduced by Polyansky. So that's the landscape for these. And now I stop here. That's some background and pertinent reference for this section. And I believe you have access to the slides, so there are more there for your perusal after the talk. And maybe this is a good time for me to stop and let people ask questions if they have questions. Do you have any questions? Okay, then I have a question for the organizers. So the presentation, the tutorial is somewhat sectional. If we have some flexibility in the break, then it's probably good to start the 30-minute break now so that we can start with a fresh section. If that's okay with everyone, then maybe we can take our break right now.
Hi, sir. Actually, I have a question. Like, can you please explain that SIC decoding scheme again? Like,
yeah, I'll be glad to. So you're welcome to stay if you would like to stay, but also people should have the ability to take their break. I'm going to go back and explain this successive interference cancellation again here.
Here, my question is like,